So today we have with us a very distinguished guest. We have with us Dr. Vivian U from the University of California Irvine. Dr. Yu did her undergrad in Caltech, after which she moved to the University of Hawaii, where she obtained a PhD. After she came back again to the sunny California, where she was a postdoctoral fellow working on the 30-meter telescope project. And after that, she got the Chancellor's postdoctoral fellowship. And after that, she moved to University of California Irvine, where she's now a researcher, staff research in there. And today, well, she's an expert in the properties of active galactic nuclei and their impact on their host galaxies, basically. And today, she's going to talk about insights of multiphase feedback and galaxy mergers.
Okay, well, thank you, Tanya, and thank you, everyone. It's great to have this opportunity to visit this beautiful island and country actually for the first time. So I'm very excited, even though the travel was a little bit long and tedious yesterday, but I got through it and I'm ready to enjoy myself now. So I like to start off my talk with this image of the merger BB114. This is an image taken by Hubble Space Telescope, and you can see that on the western side, you've got a star-forming galaxy that's a part of this merging system, where it looks like a little octopus with like tentacly spiral arms, very bright, star-forming regions and all. And on the eastern side, it's actually a component which looks a lot more muted. It is red. It is hidden behind dust lane. And if I were to flip it now, I know it doesn't do it the first time. To a JWST image, you can see immediately a lot of the light is now coming through the dust. You can see the eastern component really well. And I'd like to show this little video because, JWST as graded, it is very sensitive, perfect for, discovering high redshift galaxies, Z of 15 or above, or I don't know what it is these days. But it is also really useful in showing us, uncharted territory behind the dust screens that even in a nearby universe where we haven't really seen before. So in this talk, I would like to first motivate why I'm interested in galaxy mergers and trying to understand their role in galaxy evolution. And then I'll show you a little bit of the results that we've been getting with Keck in the pre-JWST era. And then lastly, I'll show you, some of our recent JWST results of these galaxy mergers. So I like to start off with this medal plot. A lot of you probably have seen it before. It's showing the star formation rate density as a function of redshift, where a lot of the star formation activity is happening in this period that we call cosmic noon. And so if you break this curve down by population, then you actually see that what dominates a lot of the galaxies beyond a redshift 0.7 or so, all the way to cosmic noon, are these galaxies called luminous infrared galaxies and the ultra luminous infrared galaxies. So just what are these lurks and U-lurks, and why do they seem to play such a prevalent role in our cosmic history? And so in the nearby universe where these galaxies are relatively rare, they tend to be represented by galaxy mergers. And so as we understand from galaxy mergers, a lot of times it involves gas-rich star-forming galaxies that are engaged in a gravitational bound system, and then they're going to go through this dance where materials start to lose angular momentum, and they all fuel to the center of the galaxy that actually then triggers a lot of the nuclear activity in both star formation and black hole. And then eventually, and all of that actually happens behind dust. We have a lot of dust in the center of these galaxies as well. And then all of that eventually gets blown out by the central quasar, the luminous region in the center. And this is not the only way, obviously that galaxies transform, but it is an efficient way for galaxies to transform from like star forming spirals all the way to these red and dead elliptical galaxies. And we have since then, also rely on simulations to place this merging sequence into the time frame of about 1 to 2 billion years. So this is a short, ephemeral kind of state of a galaxy's lifetime, but it is very important and very transformative. So it's important for us to understand how this happened to see how galaxies have evolved since in cosmic time. And you can also see that during this period of time where the star formation activity and black hole growth is changing a lot, they actually somewhat correlated as well. And this kind of gives us some hints as to how this coevolution of black holes and galaxies happen, that we know there's some feeding and feedback going on. And so my research focuses on understanding these galaxy mergers in the small scale type of physics sense. And so in order to really understand how these processes are related to each other, we need to think about galaxies not as static entities, but that they are dynamic systems. And so I like to, borrow this plot from a lot of Google graphic you can probably find these days, but this is a good illustration of how galaxies are part of the cosmic ecosystem, the way we understand it, with star forming gas, condensing down into star formation. We have a lot of active star forming galaxies that contribute to the luminosities that we've seen. And then as these stars evolve and they explode as supernovae, and then that can blow out winds and also enrich the interstellar medium, which then cools back down to form the next generation of stars. But some of these also goes out of the plane, the galactic plane, and potentially recycles back. But also some of it may get removed if the AGN in the center is energetic enough to drive these outflows. And so exactly how these processes and how the energy exchange leads to different results in galaxy evolution. And also, what role does merger play in all of this in changing some of these aspects is what I'm interested in studying. And of course, we've seen some simulation work. This is a little bit dated now by simulation speak, but this is one simulation from the FIRE team where they were simulating what happens when in a galaxy merger. On the left, you have the stellar component. On the right, the different colors here represent temperatures, different temperature gas. And so you can see that, with the reason why we want to think about this as a multi-phase, multi-scale kind of problem is because there are a lot of different parts involved that includes different, phase of the gas and different temperatures of the gas. And what that is happening is not necessarily co-spatial with each other. And so we need to really understand the detail in that level. Okay, so to that effect, so I'm part of the GOALS collaboration, the Great Observatory All-Sky Alert Survey, where we've amassed a sample of 200 of the local brightest nearby luminous infrared galaxies, a lot of these, again, galaxy mergers. And we wanted to understand this as a population level to understand how this process happens in the nearby universe where we can actually resolve details. And you can see that we are a very international team, and some of the members here include our esteemed colleagues in the room as well. And GOALS is a multi-wavelength survey, and I would I'm happy to add that we're actually now a multi-messenger kind of survey. So besides the full range of the electromagnetic spectrum from X-ray to radio that we span, we also very recently have a neutrino paper starting some collaboration with some of the IceCube folks. And obviously I'm not an expert on that, but happy to chat a little bit about it if you're interested. What I have more of an expertise in is the optical and infrared regime, particularly with the Keck telescope and the JWST. So I will be focusing more on those results. Okay, so back to this gallery, because I really like it a lot, and it really shows that the sample of the gold sources do span a range of galaxy merger stages, from early stages all the way to coalesced and post-merger stages. They span a range of infrared luminosities. And so, by doing this in a statistical sense, we can actually then build up and understand these processes statistically. So I do want to focus on a few of the case studies. So I'm going to start with my favorite ULERC. This is a McCarran 273, kind of like a little toothbrush here. And I mentioned that I use the Keck telescope. In particular, I use integral field spectrographs, one of which, the OSIRIS instrument, is a near-infrared IFU behind AO. And so with adaptive optics, we're able to focus on really the nuclear gas kinematics that we're seeing happening in these galaxy mergers. So McCarran 273, it's special in a lot of ways, but one of the ways is it does have an X-ray AGN in the center, and we also have multi-wavelength data that points to this. The nature of this kind of diffuse gas was debated a lot, and I'm going to show you what we found about it. And so here is what the OSIRIS data looks like for McCarran 273. I'm showing the image here. That this is the H-band continuum, and then this is the slice in the H-band. So if I kind of go across the slice, you can see for the iron 2 line that's detected in this structure, you can see how the gas was moving. And because of that, so if we were to map this onto a 2D frame, 2D work. So here again is the flux map of that iron 2 gas I was just showing you. The contours are from the H-band continuum, and you can see that the AGN that we knew is in the southwest region. It's very, very bright, but the northern part looks a lot more diffuse. And there's actually a really brightly peaked clump here in the southeast in iron 2, and that's actually caused a little bit of active research, so to speak, and I won't be talking about it here, but we can talk a little bit more about it if you're interested. So with the data that we've gotten, which is a very, very high resolution, we had 35 milliarc seconds with the plate scale and about 50 milliarc second full width half max. We are actually resolving within the sphere of influence for this black hole, and you can see this is the velocity map that that I was just showing. So this is showing actually Keplerian rotation around this remnant nucleus. And so with the resolution that we get, we were able to model this with Keplerian rotation, and we got a black hole mass of about 1 billion solar masses. And this actually matched really well from a estimate that other people have gotten using OH maser before. So we're pretty happy with the way that we were able to get this measurement. And I will mention that using gas emission to measure dynamical black hole masses has pros and cons. For those who do stellar dynamical black hole measurements, that gas is maybe arguably less reliable because it's subjected to more different type of motion going on. But at least in these galaxies, we were able to see a lot of the orderly rotation in the nuclear gas disk, and allowing us to measure black hole masses where we felt comfortable that we can resolve within the black hole sphere of influence. And because of this, and I should also mention that because we were able to deduce such a massive object in the center, it allows us to argue in favor that it does, even though we couldn't see it, it does argue, we did argue that this contains a Compton thick AGN in the center. And later on, with very deep Chandra observations that we got because of these results, we actually were able to confirm the dual AGN nature in this system. So with the way that we could measure black hole masses using gas dynamics in these galaxy mergers, then we were able to answer another question where we've seen these black hole scaling relations that says black hole masses and their properties of the bulges that they reside in this case the stellar dispersion, they seem to be tightly correlated for normal galaxies. But where do these galaxy mergers fall? And so using this method, looking at a number of different tracers with the gas, with the stars, we, in our earlier part of our campaign and looking at late stage mergers, we actually found that a lot of our mergers seem to fall either on top of or above the black hole scaling ablation. And this was something, it was puzzling to us because, well, it's puzzling because it seems to be implying that black holes, as they go through the galaxy merger phase, they seem to be overmassive, and it probably implies that there's a lot of gas coming into the center before, you know, all of the large scale galactic components virializes. And so, you know, this is one of our early results. We try to verify this in other ways. And so later on, we actually got high resolution ALMA data to try to measure the gas mass within the same region. And at least for one of the galaxy, NGC 6240, which is the triangle here in this plot, we seem to be able to, you know, potentially correct for a little bit of the massive conclusion, at least for this galaxy, where we think that maybe the gas is residing within this region where the black holes can accrete on, it can accrete onto the black hole, but maybe it's not actually accreted onto it yet. So we're still trying to verify, you know, and understand if this is indeed the process that we see galaxy mergers going through. Okay, so let's back to Macarian 273 for a second. We didn't just look at, you know, iron 2. We looked at other lines as well. As I mentioned, it's important to look at the different phases of the gas. So here we're looking at the molecular hydrogen, also visible, accessible to us in the near infrared. And again, you can see very similar morphology. There's no peaks in this southeastern point here, but then you can see that same rotation. But what's really interesting here then is the dispersion, where we actually see some enhancement kind of going in the cone shape along the minor axis of that disk. And so what we're seeing is actually a signature of the molecular outflows being driven by the Compton thick AGN in the center of this disk. And we've went ahead and measured some of the properties of this outflow and velocities and masses. And so these are some of the numbers that we can then compare with the simulations at the similar resolution scales that we have. And so this is, of course, one galaxy. We have actually targeted a number of these over the past several years. And so together with my collaborator and Matt Ling in Toledo and the rest of the close collaboration, we have targeted somewhere around 30 some systems with 50 some nuclei, separate nuclei over the course of many keck nights. And so we've done a number of focus on a number of science topics, looking at molecular outflows, dual AGN, nuclear disk, black hole masses, etc., which I won't talk about here, but feel free to check out our website if you want to know more. And also I want to happily share that Anne and I just got a collaborative NASA grant starting this year, so we can continue the work that we've been doing over the next few years. So one of the other results from our the Keck survey is looking at how the nuclear star formation rate changes. And so this is thinking about, not global star formation rate, but actually star formation rate within the central kiloparsec, where it's very dusty. And so with near infrared, we're looking through, more extinction than we could in the optical. And so when we look at what the star formation rate looks like, it's a function of merger class, increasing merger class, or decreasing separation. And so we seem to be seeing this increase in the star formation rate. So this seems to imply that we are having positive feedback in the central parts of the region. And this is, I wouldn't say controversial, but it is important to think about how when people talk about mergers, a lot of interaction to remove gas from the system, but perhaps in the center and in relevant scales to molecular gas, that we're thinking about that the shocks and everything that is compressing the gas in these small regions, we are seeing increases of the star formation rate as the mergers get closer to each other. Another things that we looked at was that we found shocks. We were tracing shocks with the molecular hydrogen that we saw. And so we measure excess molecular hydrogen as normalized by hydrogen recombination line. And so we see that actually there are more shocks in hosts that the AGN hosts that that seem to imply that maybe AGN are responsible for these shocks. But when we try to compare them against some other AGN property measures like the mid-infrared or polarimetric fractions that Tanyo determined, we actually don't really see clear correlation. So it seems to be that the story is that we see shocks that are more prevalent being in AGN hosts, but we don't actually we don't really know exactly what's driving it. And so this leads me to kind of thinking about that picture where, okay, in this sample we've identified here 7 sources that have really prominent outflowing candidates, but we're still not understanding exactly how that happens, because perhaps there's still more dust that we're not penetrating through in the near infrared. Maybe there is we're curious about how the metallicity is being driven in this environment, and without a clearer picture to get into the center of these sources, we really can't answer the question that I'm interested in, which is how supermassive black holes grow in mergers. There are different pathways where it may be that the black holes, once they get triggered, is that they grow in a low luminosity state, kind of in that donut shape of AGN picture that we all have, or maybe all this growth happens in very dust obscured ways before the blowout. So I think that understanding this pathway and the time scale that this happens will have large implication of how we see black holes grow, not just in the physics sense, astrophysics of black holes, but also thinking about the missing dual AGN population that we're all kind of searching for when we think about merging black holes as potential gravitational wave progenitors. Okay, so well, then this leads me to December 25th, 2021. As we are probably all familiar with this date, it was a huge day of our lives, and in my life in particular. My baby girl was born on that day. I think there was some other telescope that got, I don't remember much about that one. Actually, the funny story was, my daughter was born early. She came like 3 weeks early. I think I was just kind of watching the launch, which was like 4 a.m. local time. And then I was about to go back to bed 2 hours later, and then my water broke. I was like, oh, okay. So much for JWST. Okay. Okay, great. So this now leads me to our JWST program within the GOLDS collaboration, where we've been very fortunate to have actually been consistently awarded time in all of the cycles that have been around so far. So in the inaugural early release science cycle, we were one of 13 teams to have gotten data on these 4 galaxies in particular, which were chosen to span a range of infrared properties, and the observations took place in the second half of last year. And so far we've got 8 papers that were published, and then we have a lot more on horizon. And then also we have scored cycle 1 and cycle 2 programs as well. And these are a little bit more targeted campaigns to look at alpha candidates in cycle 1 and all the ULERCs in cycle 2. And our cycle 1 observations just started a couple months ago, and the data has been really gorgeous. So we're very excited and very busy at the same time. Okay, so I'm going to talk a little bit about what we've seen so far with JWST. I'm focusing primarily on 7469, but I also want to give some highlights on the other 2 galaxies in this talk. Okay, so in GC 7469, it harbors an active black hole, and what's unique about it is that it has a star-forming ring at its center, so about 500 parsecs in size. So it really gives us a good case to study this AGN Starburst connection. And so here on the left is the optical image from HST, and then on the right, as you can see from the diffraction spikes, that this is a JWST image. And it's not as dramatic as VV114 as I showed in my title slide, because this is a face-on galaxy. You can see pretty well, you know, into a Seyfert 1, so you can see pretty the central black hole pretty well, but you can still see that some of those dust lanes are actually getting filled in by the infrared emission that's now peeking through in the JWST image. So we of course have actually Spitzer data for all of the galaxies in our gold sample, and so this is a Spitzer IRS spectrum, and you can see really nicely a lot of the infrared features, but for dramatic purposes, we've chosen to show the comparison of the JWST mirror image compared to the Spitzer IRS low resolution image. And so immediately you can see that we can resolve a lot of lines well, and not just, you know, additionally what lines are there, but also how, you know, line profiles, right? So that tells us something about how the gas is moving. But what I'm personally really excited about is the fact that, you know, with JWST, we now have IFUs in space, which, you know, tells us, of course, not just how what gases or species are present in these spectra, but also what they look like, what the morphology. So here I've highlighted 3 different gas species. So there's the iron 2, there's argon 2, these are ionized gas, and then the molecular gas, hydrogen in the center. And you can see that they look very different. You can see that central AGN with the star-forming ring in the ionized gas, but for the molecular gas, the ring is not as apparent. You can actually see some of the spirally structure that connects to the inner spiral arms once you overlay with the HST image. And here again are the top row are the 2 flux maps that are from the previous slide, but we also get the kinematics information. So you can see that in the velocity map there, how the ring is actually rotating, and then if you look at the dispersion, there's actually, they also look different. In particular, we can see some enhancement in the molecular gas, kind of like what we did in Mercurian 273. We further did a deeper dive into the channel 1 data. So here I'm showing a channel map that's centered, I think, at 7 micron or so, and then we've subdivided this inner ISM region into a 3x3 grid where I can extract spectra that corresponds to those grid size. And so if you do a zoom in on this particular line, magnesium 5, which is a coronal line, which has ionization potential like 100 and some EV. So this has to be excited by the AGN. This has to be what it's showing us is that it's being excited by the AGN, and this is a very highly ionized line. And you can see that these lines have extremely blue shifted profiles. And so what we're seeing is that there is highly ionized winds driven by the AGN kind of coming out from this eastern region, but also it's a face-on galaxy. So we can see it in some of the other parts as well. We looked at what this asymmetric profile is seen in the high ionization line, but not the low ionization line. So here I'm showing, you know, in together all of the high ionization species, and then the low ionization species. So you can see that the blue shifted profile only exists for the high ionization species, but not in the low ionization species. And then the molecular lines are actually pretty narrow as well. And when we plot up the line widths against the ionization potential, we're really seeing a decelerating stratified AGN-driven wind, and we've done some estimation to look at the black hole accretion rate based on the O4 line, and I'll come back to this point in a few slides. We also looked at you know, how the molecular hydrogen, the excess molecular hydrogen, might fare with compare with the shock tracer iron 2, both ionized, both normalized by the pH in one case and the hydrogen recombination line in the other case. And we see this correlation, which seems to suggest that the shocks that might be excited by shown as traced by these 2 gas species are correlated. So they're probably sharing the same origin. And so the story that we've put together for this system is that we're seeing kind of an outflowing gas from the central AGN that is dumping energy into the surrounding ISM through shocks, and all happening inside the star-forming ring. And so my postdoc, Marina Bianchin, is now doing some follow-up work. Actually, I wanted to also share that we just found out recently that Marina has won the IAU Gruber Foundation Prize. So I think the official announcements might come out soon. If you see that in the IAU news, you now know what Marina is working on at the moment. Yeah, so Marina was looking at near spec data. So in the near infrared, again, we have, you know, another very wealthy set of spectral features. And in particular, she was looking at some of the hydrogen recombination line, in this case, Passion Alpha, which also gives us higher resolution from near spec as well. And so what she was noticing is that there is now kind of like this spirally structure in the residuals, velocity residual that we didn't really see in the Miri data before. And so she tried to model this with a very simplistic rotation, and looking at the residuals, there seems to be some spiral arm residuals going on in this galaxy, and we compared it to some of the other papers that we've seen. We think we might be seeing some inflowing gas into the central supermassive black hole. And so she calculated the mass inflow rate and actually found that it's like an order of magnitude or something larger than the mass accretion rate that I mentioned we measured before from Miri. And so what we then are seeing is that gas is able to build up in the central kiloparsec region, which seems to be also consistent with what we have found with the Keck results before looking at black hole masses. Another thing that we were able to do with the Miri data is that this is work done by Thomas Lai, who is another postdoc within our goals collaboration, currently working at Caltech IPAC, and he looked at the PAH features that's available to us in the Miri. And so here is a PAH 6.2 micron map. From this, he did a lot of extractions around the ring, but also kind of extending into the central supermassive black hole. So this plot is very busy, but basically he was looking at pH diagnostics that tells us the size of the grains, as well as neon line ratios that tells us something about the radiation field. And what he found is that there isn't that much variations if you look around the ring itself, but if you go into and get closer to the AGN, that only the larger grains remain. So it is telling us that the AGN radiation is likely destroying the smaller grains. And this is also consistent with the wind geometry that we presented before. The reason that it's not really affecting the ring itself is because this is a face-on galaxy, so the ring's coming at us. But as you get closer to the ISM, then you can actually see the difference in the grain size. Okay, great. So moving on to VV114, which was the galaxy I showed in the very title slide of my talk. Here again is this is an HST 814 image. And if we zoom in and ignore the title tails, here's the image from the papers where we have the HST image on the left and the JWST image on the right. And if you actually look closely, it does get resolved into two cores in the JWST image. And so what we want to know is, if there's an AGN here, and if so, which one is it? Where is it? So this is the image, but now this is not just from the mirror imager, but this is from Spectra. It's from the IFU. So Jeff Rich was leading this work, and he did a lot of extractions from different parts of this galaxy. So we've identified that northeast core and the southwest core, and the red and the yellow here. And what he found when he looked at the spectra is that the northeastern core is very much absorbed. It's very much deeply embedded nature in the northeast. And so then he went and looked at the near infrared spectra. So again, here showing this, the Southwest and the Northeast, they look very, very different. And so using a combination of spectroscopic and photometric diagnostics. So here he's calculated the equivalent width of the 3.3 micron PA and plotted against the colors, the mid-infrared colors. He found that actually the Northeast core and the Southwest cores, they fall into different parts of this diagnostic plot. And so this is actually was a little bit of a surprise to us because I think based on radio or other wavelength, multi-wavelength data before, we thought that the AGN Strawberry's nature identity of these cores were the other way around. But the JWST data is showing us something different, but also even for where we think the AGN is residing now, that we still don't see coronal lines. And so what does that mean? Like, is that we've been hoping that, you know, in the community that coronal line would be kind of the telltale sign for how we can find embedded AGN. So are we still being misguided? Is this still not an AGN, or is it that there's still more dust or something else? So the other part of what I'm interested in sort of like understanding, you know, not just the nuclear gas, but, you know, how it actually might influence the rest of the galaxy. So again, Vivian 114, but this is work led by my other postdoc, Justin Cater, who has been leading this campaign of using the KEC, another IFU on KEC, the KCWI instrument, where we are mapping the low surface brightness, large scale gas in these systems. So we have JWST data in. And so here you can see the black contours is the same as the optical light. But once you, but then in the image here is showing optical oxygen to flux at 3727, which is, you know, low ionization gas. And so we actually see it all the way out, you know, 10 kiloparsecs or so from the center. And so this is really interesting because it's, you know, we're then trying to ask the question, are we seeing this gas that's actually driven by whatever nuclear activity has been going on, or is it actually always there and it's just being eliminated, or is it, you know, is it the merger mechanism itself that might be driving the gas out? And so either way, we are seeing the fact that we're seeing, you know, the gas that far out of the system means that whatever is happening from the merger, from the nuclear activity, it has the potential to heavily impact the CGM around these gases. Okay, so lastly, and quickly, I'll just show what we found for this other merging system, TUSWICI 96. This is, again, a very interesting merging. It looks a little bit like Vivian 114 in that you've got two or interacting components. And previously, what we can see is that, you know, the middle region gets resolved into multiple clumps, and we see that actually this is where a lot of the infrared luminosity is coming from. So this is a Spitzer image where you can see that basically most of the infrared luminosity is coming from this region. And now with the resolution that's provided to us from JWST, we actually can really resolve where the infrared luminosity is being dominated. And so we found that this clump D1 is actually responsible for 70% of the mid-infrared emission. And so, but what is it? Is it like nuclear star cluster, or is it the black hole? And so Hanai Hinami from Hiroshima has been leading this work. This is based on just the imaging results so far. And so she was doing mid-infrared color diagnostics to try to figure out the nature of these interesting clumps that is happening where all the infrared luminosity is coming from. And what she's found so far is a little bit inconclusive, but it's also interesting already that the interesting clumps, the D1 and D0, seem to be maybe in this inconclusive region between AGN and Cerberus, as nature would have it. And also, but then maybe it's a C naught that's kind of on the AGN side. But so it's still a mystery out there, I think. And right now we are analyzing the spectroscopic data and to see if we can actually get down to the bottom of this mystery. Okay, so that brings me to the summary slides of my talk. And so what we've seen so far is that we're seeing, multi-phase inflows, outflows, feedback, via shocks. They can all happen all at once. And so we really need, high resolution integral field observation in order to resolve these processes, to understand, the energy exchange and the feedback cycle within these extreme environments. And the mid-infrared colors and spectroscopy are really the key to recovering the embedded nature of these nuclear cores and identifying hidden AGN because of the dust that's in the center of these systems. But there's still more questions that the JWST observations have prompted, and so hopefully we would be able to answer it when we have more data coming in with more data from different systems coming in. Hopefully we'll then be able to study these processes that are happening at different stages of the merger, and so that we can start making statistical inferences to constrain like black hole feedback models, among other things. So I have listed here a summary of all the published papers so far from our campaign. I obviously didn't get to talk about most of it, but feel free to check them out on ADS, and also we will have more coming soon, I promise. But also I wanted to mention that our team has been featured on PBS Nova. I don't know if anybody here has watched it, but this was an new episode from PBS Nova that was just aired earlier this year in February, that was talking about new JWST results, titled "The New Eye on the Universe." And so let me see if the audio works, and then maybe this is just a one minute clipping. So let me.
At the California Institute of Technology, an international team of scientists has gotten its data from JWST. Just gonna launch right into it. They come together to discuss and debate what their test drive of the telescope has delivered.
We have a great team. We have people in the US, we have people in Japan, we have people in Europe, we have young people and old people.
Yeah, and then I was so this group of astronomers I've known for many years, since my graduate school days, and I would call them my family.
So for the last 2 years or so, it's been primarily meetings through Zoom, but there's no substitution for like just the energy you get having people in a room together. It's fantastic. And this is the Zoom in.
The team has gathered to figure out what JWST is telling them about one of the most mysterious objects in the cosmos: supermassive black holes.
Okay, and that's the end of the clip. So if you want to watch more, go ahead.
Thank you very much, Vivian.
Yeah.
Excellent book. Anyone has questions? Any questions? I just saw Costas. I just photos and right first. Disclosing.
I want to ask, are those shocks resolved?
Are they resolved?
Yeah, no. Do you resolve them? Can you see them in the imaging?
So we're basically using molecular hydrogen as a tracer for those shocks, and with the imaging, at least with JWST, it's a broadband imaging, so we do not get to look at just the shocks themselves. But we do have actually, now you asked it, we have HST high resolution images of iron 2 coming actually May 31st, so next week, of VV114. So we would be able to see if we can actually see those shocks in a large scale, just from the imaging itself. So ask me that next week.
Okay.
Thank you.
Yes, just. Thank you very much. I was wondering about the last slide that you showed with two different regions. Yeah, the zeros. Okay. Do you have optical data from this system? Because I was thinking all 3 points are in an intermediate state. not AGN, not starburst, so maybe it could be a composite galaxy or something like that. And maybe with optical spectroscopic data, you can see from the BBB diagram. So
Yeah, so this target is definitely on our list to get optical spectroscopy with KCWI, but I don't think we have it yet. We are getting more data. So KCWI, I'm not maybe KCWI is the blue side of Muse, and then but right now, starting this semester in August, we're actually having the red side of KCWI, which is called KCRM, on KEC, where we can do the full BPT diagnostic. So we're hoping to get basically the full set of optical diagnostics for all of our sample that have the JWST data, and then we will answer your question more fully then. Yeah.
But in the challenge is to get the necessary spatial resolution, right?
With which,
Because this is practically point sources on JWST.
Yeah.
right?
that's right.
So with Jack, can you have a sleep, which will be able to?
So-
this 0.1?
So
Could be a section, right?
yeah, I mean, probably that's a good question because with KCWI, we are looking at more the large scale stuff. So there are different settings, but we try to use the large setting to get, because we're most interested in the low surface noise brightness, large scale gas. Even with the best resolution on KCWI with a small slicer, I think these are likely not resolved in optical, not to mention they might be heavily extincted. So in that sense, that's why the optical diagnostic may be perhaps limiting in the usefulness of these galaxies. And we need, we need the mid-infrared diagnostics, but also this kind of resolution in these wavelengths so we can actually see better what they're doing. And like I mentioned, like there, we do have the near-infrared and mid-infrared data for these galaxies from JWST, and I'm in the process of analyzing them right now.
Yeah, I was gonna say, look, one of the most active line of research is actually trying to develop the kind of diagnostics that exist in the optical, like BPT,
Mhm.
but adapting them to observables in the near and mid-infrared, right? Because in these objects, you're in the optical, especially in these regions, you are only scratching the surface
Mhm.
of what you can see.
That's right. I mean, if you look at the 4.4 micron image in the blue, this is completely dark. So, yeah.
I think John, one, I don't know if you.
oh yeah, just a short question. So for 273, what's the separation of the two zones?
It's the 750 parsecs. Yeah, yeah. So sub-kiloparsec, but not in the gravitational regime yet.
This is 60 to 40.
273,
And 60 to 40 is
1 kiloparsec.
Oh, it's this one.
I was just, yeah,
Okay.
oh, no.
It's
Maria.
about the paper, 2019.
Mhm.
I want to ask you, which tracer do you use
For
to estimate the
star formation rate, we use bracket gamma. So that's in 2.16 micron. Mhm.
Okay, and for extremes.
We use the bracket gamma and bracket delta
Okay.
decrement. Mhm. Yeah. Yeah, yeah.
And in your work, where you actually do the modeling and you estimate the
Black hole mass.
supermassive black hole to be something like 10 to the 9.
Mhm.
Do you make the arms sufficiently close so that the gravitational field of the bounce doesn't affect you, and it's only, or you make an assumption?
So we
about
did,
black hole?
yeah, so for our sample, we did a distance cut. We have to limit it down to, I think, 0.05 or below, where we have, the available guide stars and everything where we can do this technique for. So that it's a sub sample of the gold sample that is observable in the northern skies. And so with that thing, so we are, at least for the ones that we have claimed to measure black hole masses, we are resolving within the black hole sphere of influence, so that all of the
All the kinematics are due to the point source in the center.
yeah.
Question? You have your own program, JWST.
Mhm.
Can you remind, I mean, just for my curiosity, that the sources that you have in your program, how they are distinct from the sources in goals?
Yes, I think it was, let me go back to this one. So, yeah, so, well, I have, let me see. I have another, let me see if I can. I was just looking at this earlier today for someone else, but let me show this one. So these are the sources that I show in our cycle 1 program. And these were selected looking at X over bracket gamma on the near infrared and X over pH from IRS from Sabrina's work. And so we basically, this was our selection for the cycle 1 program. So these have high X over pH that's higher than what the PDR models allow. So, and then also in the near infrared as well. So this was how we have selected the cycle 1 targets and compared to the other sources.
So basically dominated by shock excitation.
That's right. Dominated by shock excitation, and also in the near infrared, the OSIRIS data that we saw some hints of there being coherent of outflow light thing.
And coming back, I think to Costa's question, I think, well, most of the H2 is resolved, right? But we don't see any kind of like lower structure that you may look at, like bow shocks. I think it's more on what are the physical resolutions, like 100 parsec resolutions?
So with OSIRIS data, technically we have 50, we have slightly better than 100, maybe like 60 to 80 parsec, depending on the condition of the particular night. But yeah,
these scales that are sufficiently small to
yeah.
Feedback on stellar, but maybe in galaxies where you know that the AGN is not.
Yeah, that's right. I mean, CAC has a much bigger mirror than JWST, but we're looking through the atmosphere, so a lot of times we're a little hampered in that sense, in sensitivity and things like that. Yeah, exactly. So hoping that's why JWST is going to be awesome and complement our CAC data.
Yeah. Could you say a few words about the neutrinos?
Sure. So again, this is not my expertise, but basically, some members of our goals team were talking to the Ice Cube folks, and they were trying to, and because I guess partially it's motivated by the fact that the neutrinos have been detected in, or at least in the direction of NGC 1068, which is a low luminosity, which is a Seaford, in our goal sample. And so there's probably some theoretical basis for why we think that they're more likely to be neutrino generation within LURCs and ULURCs, which happen to be also more star formation. They have star formation rate above 100 solar masses or something. And so the paper that I listed right now is a more presenting a framework where we're thinking, okay, if we're assuming a certain neutrino generation rate based on supernovae, and we can make estimates based off supernovae in these galaxies, is that enough to account for the neutrinos that we might have detected, coming from galaxies like 1068? And I think the short conclusion is that probably not. I think the AGN is probably have a lot to do with having accelerated those particles, seeing generate neutrinos. So then I presume in following work that they would, also incorporate the calculations for AGN into in this framework.
I think the signal, it was a stacking analysis of all the galaxies.
Yeah.
No signal, but yeah, the stacking was not sufficiently deep still, I think, to say anything. Of all the galaxies in the like 200 galaxies
In the goal cell.
both in the goals and in the neutrino, excluding JWST.
These are PEV neutrinos with good localization. We know there's physical this kind of thing. don't know, there are many, there's one with time information from an ancient and. But these would be steady sources. I don't think it's-
Was a dungeon.
That's right.
But the results of this study is something like the average behavior of the population, right? I'm not saying. Based on the, maybe it's not based on given the high resolution data that we have from JWST, can you say something about the role of the metallicity in these amazing galaxies? Because so that we found enough metallic lines, so maybe.
Yeah, that's one of the goals that we want to do with at least the cycle one program and probably with the rest of our data as well. There's just so much information. We haven't gotten to the metallicity yet, but yeah.
And you can make metallicity maps of the.
Yeah, I mean, as long as we have sufficient signal to noise for all the metallicity line, yeah, that's what we want to do.
Okay, let's thank again Vivian. And if you want to talk to her, she's in the.
Thank you.
Thank you for
That
coming.
was exciting time.
Thank you.
Thank you.